We're very pleased to have Nikkil here with us today. We circulated his CV in advance, so I won't give a super long introduction, but he's no stranger to Berkeley. He got his undergraduate degree here at Berkeley in interdisciplinary studies. He went on and did an MPH in global health at Emory, and then he went on to Penn, where he got a master's in statistics and a PhD in demography, and is currently a postdoc at Harvard in the population center. So I will let his research speak for himself and let him get on with the show. So thank you all for coming.
Thank you. So good afternoon, everyone. Thank you all so much for coming. I'd like to thank the committee first for inviting me here today. It's a real honor to be able to share this work with you all. So my talk is on the population health benefits of blood pressure, but I'd like to motivate it with something that I think we all here can agree on, that improving life expectancy is a major global health policy goal. Now, my interests in particular are in aging low and middle income countries, places like India, Indonesia, Mexico, and South Africa. And these countries are undergoing two really big transitions right now that are going to shape how future mortality achievements are made. So the first is an epidemiological transition, where infectious diseases of childhood are giving way to a rising burden of chronic non-communicable diseases that primarily affect adults. So as child mortality declines, gains in life expectancy are going to have to start coming from the adult ages. The second thing is these populations are also aging. So if we think of the burden of mortality as the share of deaths attributable to any set of causes, as populations age, the share of deaths attributable to adult causes is almost mechanically going to increase. So in the background of these two important transitions, I think the big question faced by these countries right now is what should be prioritized and where should we start? And that's the question that really motivates this research and a lot of my other research as well. I'm going to argue today that I think addressing blood pressure is a really promising place to start, and that can have large gains in mortality at the population level. An important caveat, though, is, of course, I'm not the first person to ask this question by the long shot. Entire programs like the Global Burden of Disease, in some ways, are built to answer these types of questions. So one thing I'm going to touch on many times throughout the presentation is I think the methodological approach that I'm developing here has a few distinct advantages over the GBD-style estimates. So a bit of background on blood pressure. High blood pressure is known as hypertension, and it's a major cause of mortality. At the individual level, it significantly increases the risk of mortality from stroke, coronary heart disease, and other cardiovascular diseases. And all of these are somewhat leading killers in the world, so it's perhaps unsurprising that in countries where we have comprehensive vital registration data, hypertension is a major risk factor for mortality at the population level. And one thing I'm going to argue throughout the presentation is that even in countries like Indonesia, where we don't have vital registration data, that hypertension is still an important thing to consider. Despite this really high burden, though, the causes of high blood pressure are pretty poorly understood. Most cases are classified as what's known as essential hypertension, or hypertension that wasn't the result of some other underlying health condition. But a lot of clinical trials and observational studies have established a few important risk factors. So the big three are diet, weight, and physical activity. And here, diet is not just salt, but other macronutrients as well. But beyond these big three, the evidence starts to get murky fast. Smoking is actually a surprisingly controversial risk factor for high blood pressure. And while it's true that it certainly elevates your blood pressure in the short term, it's not actually clear that it leads to chronically elevated high blood pressure. And now a lot of studies are looking into the role of stress, socioeconomic status, and genetics, but I think it's still an empirical challenge to get good causal estimates of these and to understand the mechanisms they operate through. So there is, though, one risk factor that's basically important in every population it's observed in, and that's age. That in the absence of blood pressure medication, blood pressure rises really linearly and steeply over age. So we expect that as populations age then, blood pressure is only going to increase in importance. So I've painted kind of a dire picture here. It's very important for mortality, but we have no idea what causes it. But thankfully, decades of clinical trials have shown that treatment to reduce blood pressure is really effective at reducing the adverse mortality consequences of it. So whether or not, despite the fact that we don't necessarily know what causes it, we know that treating it can reduce the mortality risks associated with it. So of course, I haven't spoken now to how important this is in developing countries, places like India and Indonesia. And unfortunately, hypertension and a lot of other non-communicable diseases suffer from a lot of misinformation. The first is that hypertension is a problem of rich countries. And this just frankly isn't true. All the studies that look at this find very high levels of hypertension in low and middle income countries. This study, for example, finds that among adults, over 50% in all 5 of these countries are hypertensive. The second big thing is that hypertension is a recent phenomenon that's being driven by changing behaviors and westernization. And while those things are probably not good for hypertension, all the evidence seems to suggest that it's been around for a lot longer. So if you take a look at rural Indonesia, levels of blood pressure have remained high and virtually unchanged for 20 years. And the final big piece of belief is that hypertension is a problem of rich people in poor countries. The typical narrative is really this urban elite, the one who's very westernized and is very sedentary. But that also doesn't seem to be true. And I'm going to highlight 2 studies here that I'm familiar with. We're finding that in rural Malawi, blood pressure is very high among poor, primary agrarian populations. So these are people with very little Western connections, and they're very lean and quite physically active. I'm also affiliated with the Health and Demographic Surveillance site in India, and they find there that stroke is the leading cause of mortality for both men and women, and it's killing people at very young ages, in their 40s and their 50s. So all this together really seems to suggest that in these countries, there potentially is a really large burden of mortality from high blood pressure. But my talk today is, of course, on Indonesia, and I want to provide a little bit of background for Indonesia, and I hope to convince you of 2 things. The first is that blood pressure is an important thing to consider for Indonesia, but also that the lessons we learned from the Indonesian context might be applicable to a broader set of aging low and middle income countries. So this is Indonesia. It's a large country. It spans 2,000 miles across. And it's actually an archipelago. It's made up of over 15,000 islands. And Indonesia is a populous country. It has a population of around 250 million individuals. So that makes it the 3rd most populous country after China and India. It's about 50% urban, and life expectancy at birth is around 67 for men and around 71 for women. And child mortality is still slightly high. So if you look at, say, E40, it's a little bit higher. It's around 32 for men and 35 for women. But the big thing that's happening in Indonesia right now is that it's aging really rapidly. So if we take the share of the population above age 50, this is expected to grow from around 17% to almost double, to 31% in just 35 years. So the magnitude of this population aging is really rapid. As a reference, the US is only expected to age by about 6 percentage points over the same period. So this seems to suggest that adult health and adult causes of death are really going to become more important over the coming decades. Now, one way to look at how important adult health is right away is to look at the cause of death structure of Indonesia. And I wish I could say it had a vital registration system, but unfortunately at this point it doesn't. So these are estimates from the World Health Organization. But I think as just a first pass for understanding the causes of death, these are useful. And I'm going to not so suggestively highlight 4 causes of death here. That's stroke, chronic ischemic heart disease, hypertensive heart disease, and kidney disease. And of course, the thing that all of these have in common is that they're the result of hypertension. So without knowing anything about the prevalence of hypertension in the population, this already starts to give some impression that it might be important in Indonesia. Another way of looking at this is across the treatment cascade, or the continuum of care for hypertension. And this gives a little bit more information about how important it is in this context. So I'm turning now to data that I'm going to be using for the rest of the paper from the Indonesian Family Life Survey. And among adults over the age of 40, almost half are hypertensive. So already the levels are really high. But what's shocking is actually less than half of those individuals are even aware that they're hypertensive. So right away there's this very big shortfall in just the awareness of the disease. There seems to be some good news that if you look among those people that know that they're hypertensive, around 3/4 of them report that they're taking some form of treatment. But unfortunately, among those that are taking treatment, less than 1/4 of them actually have their blood pressure under control. So if we look across the full continuum, among adults, around half of individuals are hypertensive, but only about 6% of those people have their blood pressure under control. So I want to return now to that question that I posed in the beginning of what should be prioritized and where should we start. Levels of blood pressure are very high and very uncontrolled in Indonesia. And we know that treatment to reduce blood pressure is really effective at reducing the adverse mortality consequences of hypertension. So these 2 things together point to really large unrealized gains in mortality at the population level that could be achieved through better blood pressure control. But the real limitation is, to date, direct estimates of the size of life expectancy gains from reducing blood pressure are really unclear. As I alluded to earlier, there is a literature in this area, and it primarily uses the population attributable fraction as its measure of population mortality burden. And the PAF measures the share of mortality that would be averted if some risk factor like hypertension were brought to an ideal level. And there's nothing actually inherently wrong with the PAF. The current limitations are really more data-driven than anything. That in low and middle-income countries, inputs to the PAF are heavily modeled. For example, they use modeled mortality rates, indirect and modeled risk factor information, extrapolating from other populations or pooling over multiple populations and smoothing, and effect estimates of the relationship between blood pressure and mortality that are drawn from cohort studies in the United States or meta-analyses across countries. So for any specific population like Indonesia, it's not actually clear that these estimates are valid for a particular country. They're also given very strong causal interpretations without a lot of evaluation for whether that's justified. Also, the current estimates just don't speak to more realistic scenarios. The PAF scenarios are generally very idealized. If you move blood pressure to a perfect level or you hit some global target. And while I think those are important things to know, policymakers often want to know the gains under more realistic scenarios. What if only 30% of hypertensive individuals got access to this treatment? And what if they had imperfect control? They weren't able to get it to perfectly to 125, but they reduced their blood pressure by 5 points. How many gains would there be then? And our current estimates just really don't speak to those type of scenarios. Yeah?
Could you say a couple more words about the PAF measure? Does that take, so if you eliminate one cause of death, how do you know how vulnerable those who didn't die from it are to other causes of death and so on?
You don't. And that's actually a big criticism of the PAF approach, is that if you sum the percentage, so if you have 5 or 6 causes, and eliminate and do these exercises of eliminating everything. When you then sum the contribution of these 5 or 6 causes, it's often well over 100%. So that's actually a big limitation of this, is that it's not internally consistent with other causes of death. There's this issue of competing risks. Yeah. And so the final thing is these approaches don't identify the social or subnational distribution of benefits. And I think that's particularly important in the developing country case, because governments and policymakers often want to prioritize conditions that are more salient for poorer individuals. So if I'm a health minister in Indonesia, I could look at these data and say, yeah, well, 50% of individuals are hypertensive, but they're really more the richer individuals. So it's not my responsibility to craft social policy to address that. But there really hasn't been empirical support in favor or against that sentiment so far. So I think the big contribution of this paper is to address these 3 important limitations in the literature, while also providing an important methodological contribution that I'll talk about in the coming slides. So the first question I'm going to ask is how many years of life expectancy would gain if all blood pressure was brought to an ideal level among all adults? Now this is admittedly the ideal scenario, but I think it's an important baseline scenario just to understand the importance of blood pressure in this population. But I'm then also going to turn to more realistic scenarios and ask how many years would be gained under scenarios where there's partial compliance or control of blood pressure. And I think, yeah.
What would be the ideal blood pressure?
Systolic blood pressure of 125 is what a lot of the studies are finding now for those without coronary heart disease. And so the one thing I want to say is that for these first 2 scenarios, I'm going to estimate it with a methodological approach that's direct. So I'm not indirectly drawing and extrapolating from multiple populations. And I do this by applying this causal inference estimate approach known as the parametric G formula from epidemiology into these more traditional demographic population models. And the final thing is I'm going to look at, really speak to the equity concern and ask, are the benefits of blood pressure equally distributed across the population? Or are they really concentrated among these wealthier segments, as many people often assume? So the data I'm using are from the Indonesian Family Life Survey. It's a large household-based individual-level survey that collects extensive health, demographic, and economic information on both individuals and households. The survey's been operating since 1993, and there's 5 waves now, so it's really a long and pretty rich panel that's representative of 83% of the Indonesian population. So specifically, I'm using data on adults over the age of 40 from the 2007 wave, using the 2014-15 wave as a follow-up, for a total sample size of around 10,000 individuals or 75,000 person-year observations. And my primary outcome, of course, is mortality in the adult ages. And the way this is measured in the IFLS, if an individual in the 2007 wave died between the 2 waves, a close household family member was asked to report their date of death. So using information on their date of birth and their date of death, I construct person-age observations for each individual with a measure of exposure time lived in each age. And one thing I want to say is death wasn't a very rare event in this population. It was around 1,200 deaths, so about 10 or 12% of the sample. My main exposure is blood pressure, and both systolic and diastolic blood pressure were measured 3 times over the course of the interview by a nurse using an arm run device, one of those inflatable arm devices. And I follow the procedure that the World Health Organization recommends, where I throw away the first measurement and take an average of the second and third. The first is thought to capture what's known as white coat effects. And while I have both systolic and diastolic blood pressure, I'm going to focus really on systolic blood pressure throughout this. And that's because of a lot of evidence that shows that systolic hypertension is really what carries a lot of the burden of mortality. The diastolic blood pressure kind of levels out in midlife. And for some analyses, I'm also going to use hypertension as it's clinically defined, based on the current thresholds of 140 or 90. Interestingly, actually, this was lowered a few weeks ago, and it's created a lot of controversy. But I'm hoping to avoid that by using the old cutoffs for the sake of this presentation.
So when people say blood pressure is this over that, systolic is first.
Yes, so that's the first number, yeah. So I also include a number of control variables that I think are important potential confounders of the blood pressure mortality relationship. The big three I alluded to before, of course, diet, weight, and physical activity. So for weight, I use body mass index, but I also explored things like waist to hip ratio and waist circumference and didn't really find a big change. For physical activity, I'm looking at the report of the number of times an individual engages in physical activity in a week. And of course, diet here is the big one that's missing. And unfortunately, the diet data in the IFLS are just not that great. But I think I can at least partially capture that by including some of these more distal things that shape dietary behaviors, like where a person lives, their religion in particular, marital status, and some socioeconomic characteristics. So I think these variables are capturing some of the more distal, long-term exposures that an individual is exposed to. Yeah.
But surely those are also drivers in other ways of mortality, so they can't just capture the blood pressure diet effects.
No, they aren't. And I think that's actually part of the reason that's important to adjust for these, because they might lead to mortality through other types of causes. I mean, occupation might be one that confers excess risk for a lot of reasons. Yeah?
Sorry, do you control for other comorbidities like diabetes?
So yes, in alternative analyses, so in this wave of the IFLS, diabetes is self-reported. The newer one has dried blood spots, and they're looking at that. So the newer wave finds actually a pretty low prevalence of diabetes in Indonesia. It's still, the population is pretty lean, as I'll show. But in here, I have only self-reports. So I have self-reported stroke, diabetes, and other heart problems. And I included those comorbidities and didn't find a change, but they shrank the sample size a lot. So for the sake of that, I didn't include them here. So I'd like to actually briefly go through the methodological approach. And this is something I'd love to talk about more afterwards. It was really exciting for me to put this together. I think I could probably spend the entire seminar talking about this. So my main empirical question is how many years of life expectancy are gained from controlling blood pressure? Now, life expectancy, of course, is a function of age-specific mortality rates. So the first thing I can do is condition on hypertension status to just expand those rates. So here, EMIJ is the expected mortality rate for an individual I in sex J. And you can see that it's just a simple weighted sum of the mortality rate of normotensive individuals and the mortality rate of hypertensive individuals, weighted by the fraction of the population that fall into those two categories. So if I want to consider a really simple theoretical intervention now, where I take all hypertensive individuals and move them to be normotensive, what I need is that for each age, I need to estimate an age-specific mortality rate where no one is hypertensive. And I'm calling that here EMIJ star and expanding it as I did before. And you see the first term is exactly the same. It's the mortality rate of normotensive individuals. But the second term now is different. And here I'm introducing potential outcomes notation. So this operator in brackets refers to setting hypertension to 0. So the second object becomes the mortality rate of hypertensive individuals if they were instead set to be normotensive. And of course, this is an unobservable potential outcome. And I think for many people in this room, it'll look very familiar. In the treatment effects literature, this forms the basis of the average treatment effect on the treated. But the reason why I actually wanted to go through this exposition and not just say I'm estimating the ATT is the thing I'm after is not just the ATT, but actually EMIJ star. So this estimand is a combination of both an observed and an unobserved counterfactual potential outcome. And I think that makes it kind of unique and worth going through. Yeah?
Do these expectations include probabilities of transition between the two states?
Not here. This is for like a snapshot, a baseline, just in the 2007. But you could think about generalizing this to a multi-state framework where they transition back and forth, which is something I've tried doing. So you estimate now a series of transition probabilities where at baseline no one was hypertensive. But this is just the snapshot at 2007. So of course, this potential outcome of what the mortality rate of hypertensive individuals would be if they were instead normotensive is unobservable. And the approach I'm going to use to try to recover that is something that was developed in epidemiology in the 80s known as the G formula. And for I think many people here it'll look very familiar. It's very, very closely tied to the demography notion of direct standardization. So what I'm going to do is find a set of variables that make the assignment of hypertension status conditionally independent from the potential outcomes. So that's a mouthful. Basically what I'm saying is find a set of X variables that when conditioned upon, the mortality rate of hypertensive individuals, if they were instead normotensive, is just the observed mortality rate of normotensive individuals. And I'm going to estimate this conditional expectation using a parametric model, in this case a Poisson regression for mortality. And so what this is giving me now is an entire range of potential outcomes, conditional potential outcomes. But what I actually need for EMIJ star is that unconditional potential outcome of what mortality for hypertensive individuals would be if they're instead normotensive. So I have to integrate out these X variables, and I do that just through a really simple reweighting procedure. And this now gives me an estimate of that potential outcome. So I think for many people, as I said, this will seem very familiar if it looks like direct standardization. But I think this formulation has a couple really important advantages that I take advantage of. Yeah?
Is this also analogous to propensity score weighting?
It's It's equivalent to inverse probability weighting.
Okay.
Yeah, in some ways, yeah.
And the causal nature of this is dependent on your control variables controlling for everything, and
Yeah,
there be
so-
no omitted variables or anything like that?
That is a very strong assumption, and so the one thing I wanted to say is this leads to an analytic expression to conduct sensitivity analyses, this framework, and that's something that I'm going to take advantage of to try to simulate unobserved variables through these findings to see what happens if there's departures from that identifying assumption. Any other questions? Okay, so I'll move on. So I want to actually talk about the scenarios that I'm going to be looking at. So the first one I alluded to is this ideal blood pressure control scenario. What happens if life expectancy would be if you brought all individuals with an elevated blood pressure here, a pretty low threshold of 125 systolic blood pressure, and brought them down to that ideal 125 mark. So the way I do this is I first estimate a Poisson regression of mortality on the person age observations, including an offset for exposure time within each age. So I'm estimating rates here. I then use the model to predict the counterfactual conditional mortality rates for each combination of the covariates that exist in the data. So here's setting those with the systolic blood pressure greater than 125 down to 125. And then integrate out those x variables through weighting. And this gives me that estimate of the potential outcome that I can observe. And then,
So are you assuming that distribution of x variables in your survey is
representative, yes. So that is an assumption that it's made. And the uncertainty that is characterized, I use bootstrapping to try to characterize that uncertainty.
Okay.
But I think that's an important point, that this method won't necessarily work if you have a non-representative sample. Yeah.
I think I'm missing out on the simple idea here. So we have a coefficient for systolic blood pressure, and now I set that at 125 for everybody, and I get predicted mortality, I have observed mortality. That difference would be my naive estimate of the effect. I haven't integrated anything out, I haven't reweighted. What's wrong with
Why do you need to integrate out?
Yeah.
Yeah, because if this was a linear model, then the effect of that systolic blood pressure coefficient wouldn't depend on the values of the other covariates. But because the Poisson model is multiplicative with respect to the covariates, the ultimate counterfactual mortality rate you have will depend on what the value of your covariates are. So there's actually an entire set of counterfactual mortality rates, rather than just that one change that would occur if they were separable that way. So you're getting an entire series, and so you have to say, like, for an individual of certain age and sex, their counterfactual mortality rate is actually different than if it would be for someone of a different age and sex.
But isn't in logs this is linear, right?
Yeah, but what I need is the EMIJ, the actual mortality rate.
Okay.
And that requires that nonlinearity transformation.
So the idea is if I would have mortality, you're saying, well, having mortality means different things for different people, and so this weighting is going to say how much
Exactly.
it means for the aggregate.
Exactly. That's exactly what it's doing. So then I form the counterfactual overall mortality rate. So at this point I have a set of observed age-specific mortality rates and counterfactual age-specific mortality rates. And I can construct period life tables with both sets. And that gives me the contrast of life expectancy as it is and life expectancy as it would be in the world where all blood pressure is brought down to this ideal level. Yeah?
Given that you started the talk with sort of concern over how little we know about blood pressure and what causes it to sort of lead to mortality and what causes it to die in the first place, I'm curious to what extent you think that you can capture sort of conditional differences between treated and untreated based on observables and not incorporating.
That's a great question. So there's a very important paper that came out in the BMJ in 2009 where they look at a bunch of clinical trials for blood pressure reduction where it's experimentally manipulated. And they compare the reduction in mortality that comes from changing this clinical trial. So if you moved 10 blood pressure points experimentally, and they compared that to the observed difference in cohort studies across people at those two levels of blood pressure, and they found that the experimentally manipulated level tracked very, very closely with the observed cohort differences. So one conclusion they drew actually in that paper was that you can approximate medical effects of blood pressure reduction by making some very, very lightly adjusted contrasts across individuals, just controlling for age and sex. Yeah?
Are the mortality rates in the period life tables coming from the IFLS?
Yes.
Or
So-
are they consistent with other sources, or is that's not the only source, obviously, of mortality rates in Indonesia?
It's
or?
not, but so the World Health Organization estimates are based on this and their sample survey system called the SUSENAS.
I see.
And so this is one of the main inputs
Okay, fine.
into
So
their...
there's no other benchmarking?
There's no benchmark. So I plot, one of the first things I did was plot the mortality rates against the UN estimates, and surprised they look very, very, very similar, but it's because they're coming from the same... yeah.
I just want to follow up on the prior question about the Law et al., the BMJ study. So how would you characterize the the populations that were in most of those studies, were they from US and other high-income countries predominantly?
Yeah.
And so does that make you worried?
It makes me worry that I might actually be underestimating the contribution of mortality, not overestimating it. Because in high-income countries, the mortality from blood pressure is not just, it both leads to something like a stroke, but then conditional on having the stroke, it's the case fatality rate of having a stroke, which is a health systems dependent thing. So I think that when you take an observed relationship between blood pressure and mortality in a place with an established health system, it'll actually be a smaller number than when you take it from
So I take that point, but what about the confounders, right? So would you believe that those confounders of hypertension would be the same in high-income countries and
No, not at all.
low-income countries?
Not at all. And so the one thing I will say is I hope I will not answer this question, but give you some confidence in the robustness of the result when I simulate unobserved confounders through this. But I do include things that I think are important in the Indonesian context in particular. So there's a lot more, for example, religion is something here that kicks up a lot of variation in blood pressure, but not actually mortality. So I do think there's important context-specific confounders, but the one thing I'll show you when we move to the results, the blood pressure mortality relationship, even in the models, is very, very robust for the inclusion of these controls. It basically doesn't move. And then if I go one step further to simulate bias to the estimates, it still doesn't move that much. So I hope I can provide some...
We'll circle back to this.
Yeah, we'll circle back to this question. So the second scenario, of course, that I alluded to are these more realistic scenarios of what if only a fraction of individuals are able to reduce their blood pressure, and what if only by some sub-ideal amount. So we might think of only 30% of individuals who are hypertensive are actually able to make those reductions. And they don't bring it to 125, but they reduce it by, say, 10 points or 15 points. That second part generalizes pretty straightforward. Instead of setting someone to 125, you might think of just subtracting off 10 blood pressure points. But that first point is actually not so straightforward for the reason that I'm going to mention to you, that I mentioned earlier to you, Josh. If we think about a world where, say, only 20% of individuals who are hypertensive get the treatment, we might think of just randomly assigning 20% of hypertensive individuals and then setting there as people to get the treatment. But because these models are multiplicative with respect to the other covariates, which 20% of individuals you choose will ultimately have an influence on your outcome. So my solution to that, and ideally we would do it for every possible way that you could assign 20% of individuals this treatment. And I approximate that with a Monte Carlo simulation rather than doing it that way. So I'll go through this again. I begin starting just as I did before with the Poisson regression. But now I begin the simulation process. So I take Q draws of the data, and then within the data I assign a random fraction of hypertensive individuals to get this treatment. So if we're thinking about what if only 20% of people got it, within each draw I'm randomly assigning 20% of hypertensive individuals. I'm then doing this entire G-formula process of setting the counterfactual blood pressure, integrating out the covariates, and going within each of the draws, and then averaging across all the draws. So this gives me now my estimate of that counterfactual potential outcome of what the mortality rate would be if we now had this blood pressure control scenario that I talked about. So now I can create that same counterfactual overall mortality rate and make period life tables with the observed and counterfactual rates, and this gives me my contrast between life expectancy as it is and life expectancy as it would be under this scenario.
So you talked about running sort of realistic simulations that the policymakers would want. You think this is sort of realistic scenario?
I do actually. So I have very, I think, realistic in the sense of like, what if only 15% of hypertensive got their blood pressure by 5
But
points?
arguing that this is a random 15%, is that what we know from other countries that have been able to increase the antihypertensive drug coverage, and who's actually managing to control themselves? Is it a random sample?
It's not a random sample in that way. And so that's something I'll get to. I'll talk a little bit about the discussions. But I do think the potential for inequality could emerge here if it's the more well-off individuals that are controlling their blood pressure. But I didn't systematically set the reductions to certain people and then see. But that is actually an interesting extension of this, to set it to just say the wealthier people and then simulate it out and see if this expansion in inequality is something that we could see in other countries as well. But that's a great idea, Will.
When you create Q copies of the data, can you look are you using the sampling weights or how does that?
Yeah, I'm using the sampling weights here.
So it's like you're sampling another.
So,
Okay.
yeah.
So the bootstrap.
Yeah.
Okay.
Okay, so jumping right into the results. The first thing I want to show is just basic descriptive characteristics of the sample at baseline. This isn't the full set, but kind of the greatest hits. And you can see that on average the sample is around 54 years old and pretty evenly split between men and women and people living in urban and rural areas. And for these cohorts, most of individuals are married, around 80%. But primary schooling isn't super high. Only about half of individuals have more than a primary education. And Islam is overwhelmingly the major religion at around 90%. But one thing I want to call your attention to, these last two characteristics in particular, and this is a pattern that's emerging in many developing countries, of an almost paradox, where there's very high levels of hypertension, but kind of ideal levels of traditional causes of hypertension. You see here, the population is quite lean, well in the normal weight range, and pretty physically active as well. And I said this is something we're seeing in a lot of countries. So it seems to suggest there's something else going on for hypertension than just what those of us in developed countries would think matter, or would should be implicated. So here now I'm graphing the age-specific prevalence of hypertension for men in red and women in blue. And I want you to take away two things from this. The first is that even at young ages, hypertension is very high in Indonesia. So even among 40-year-olds, around 28% of men and 30% of women are hypertensive. And the second big thing is that this really escalates over age, to where if we're looking in the oldest age groups, around 60% of men and nearly 75% of women are hypertensive. So these levels are really striking. But one interpretation of this that comes up often when you're dealing with biomarkers is maybe blood pressure is just naturally higher in Indonesia. That it's actually not reflecting any type of excess risk, and what we need to do is revise our cut point for what we consider to be hypertensive. So one way of looking at that is to actually just look at the relationship between hypertension as it's clinically defined and mortality. So I'm showing here the results from the individual level Poisson regressions now. And the coefficients are hazard ratios. I'm going to introduce it in 3 steps. The first model you can think of as kind of bivariate plus. It just includes age. In the second model, I'm going to move to something that's something close to a causal effect by trying to include a lot of these potential confounders. And then in model 3, I'm just going to try to soak up some additional variation by using province fixed effects. So the first thing is hypertensive men are twice as likely to die relative to normotensive men. So even though this is just an association, right away this is a pretty strikingly high finding. And if I move now of including these covariates to try to get to something that's closer to maybe a causal effect, it really doesn't change much. So even after including all of these, hypertension increases the risk of mortality by about 90% for men. So this seems to right away suggest that it's not just this problem of cutoffs, that there is actually some potential excess mortality risk that's being generated by hypertension in this population.
Is it that these particular covariates just don't predict mortality in this setting, or are they completely unrelated to hypertension?
Some of them predict mortality, they're very unrelated to hypertension. So that's something I will talk to when I try to look at how it's distributed across the population, that very, very few things predict hypertension in this population other than age and sex. And so I have some colleagues in public health schools that do similar CVD research, and they mentioned to me that this phenomenon of including a bunch of social variables and seeing nothing change for the covariate is not an uncommon thing, even in places like the United States.
So does that suggest to you that there's huge error in measuring hypertension?
No, because the reason I will say that is, if I'm now looking at the relationship between blood pressure, so this is the thing that's ultimately fed into the G formula, and I've normalized blood pressure here by 10 mmHg units. This size right here, where a 10 mmHg change is related to a 17% increase in mortality, is exactly almost dead on within the range of what you observe in clinical trials. Yeah.
Is there something I don't understand? You started by saying that diet is a very important risk factor for hypertension, and that you're controlling diet by, you don't have the information, but you have these variables which are highly related to diet, relation and schooling, and here, so if that were the case, then this should have an impact, and here you don't have anything.
So I'd say they're, a priori, theoretically, we might think they're related to diet. It's not like an empirically confirmed they're related to diet. Yeah.
I don't quite know how to think about this, but if you're trying to isolate the effect of blood pressure on mortality, and people with high blood pressure may have other medical conditions that are also mortality inducing, should you be adjusting for those? Should you be adjusting for a diabetes diagnosis, for...
Right, so that...
I don't know.
You should actually, because there is evidence that the size of blood pressure reduction somewhat interacts with other comorbidities. The big one is congestive heart failure. And like I said, there is a variable in here for whether an individual reports that diagnosis, but very, very few percent, less than 2% of individuals do. So when I didn't adjust that, this didn't change in any meaningful way. But that is a good point. But I think the point is, unless you have these specific health conditions like congestive heart failure, there's still a recommendation for reducing blood pressure. When you go below 120, you start having problems of falls and things like that. But yeah.
I wanted to follow up on Will's question. I noticed that your last control is blood pressure medication, and with your previous statement, these covariates just are.
Ah, sorry, this was removed. I apologize. That's a typo. Yeah, that was. I presented it once, and this created a lot of controversy. But should you or should you not? So the way I looked at this now, actually, I apologize for that. That is a typo. But I also restricted the sample to those who weren't on reporting taking blood pressure medication, and looked at that. Then I included them and looked at that, and then controlled for it and looked at that. And all three scenarios are basically identical, but I think for just good practice, I removed it here because that taking blood pressure medication is actually very strongly related to with diagnosis and other comorbidities. Yeah.
So if my intuition here may be wrong, but if it's the case that it's mainly age and sex that predict that are covariate with blood pressure's effect on mortality, then why do you need to integrate out all these other covariates in your G?
You technically don't. So that's again like a theoretical. It just so happened in this scenario that didn't need to be the case, but I think if you're considering other risk factors, other populations with this approach, you would need to integrate out. Yeah, but
so
in this
if you had
case,
these comorbidities observed, for instance, then
right.
your approach would be helpful to.
Yeah, or something like diabetes maybe that has other important.
Okay.
Yeah.
So if I'm right, you're saying the big surprise here is that the BMI and the physical activity per week didn't suck up the variation.
No.
And and did you play around with that? I mean, given that they're so much more active and so much leaner than perhaps
Yeah, so I plotted this
European
across the
ones?
distribution.
So did you look for like thresholds and all that kind
Absolutely, I tried splines, I tried plotting.
Didn't find anything.
Yeah, no, and that's a really interesting. Also, the population is quite lean. There's very, very, very few people that are above that threshold.
Okay.
If you wouldn't mind, can I proceed? Then I'll take your questions at the end. Okay, so of course, if you take all these slides together, for women, it's slightly less predictive of mortality, and there's a big literature on this actually of why this is, and it's seen for a lot of cardiometabolic diseases. But again, it doesn't really change when you're looking at hypertension. And this slide actually created a little bit of nervousness. I thought I might have just pasted the same regression 3 times. But it turns out it's actually, this is how it is. And when we translate that into a 10 mmHg systolic blood pressure change, it's around 14% increase in mortality. So if you take the regression results and at least just heuristically combine them with that prevalence graph I showed you, hypertension is very prevalent in Indonesia, increases steeply over age, and at least at the individual level seems to increase the risk of mortality pretty substantially. So all these things would suggest that at the population level, it should be quite important for life expectancy. And that's exactly what I'm going to try to look at here. Yeah.
Well, the last slide is per 10 units.
Yeah.
But in your counterfactuals, you're moving the older people by 30 or 40 units
Only
to go down into the ideal state. So those 1.14 would be like 1.6 or something over the range that you're considering in the counterfactuals, is that right?
Yes, but I'm only moving that magnitude of blood pressure reductions in this ideal scenario I'm showing. So I do show it under more meaningful, or this assumption of 30. And that contrast between the ideal and the realistic scenario is something I'm going to actually talk about. Because I think the current estimates that we have are very idealized, these GBD style estimates of you control all blood pressure. And I think when you start seeing the gains under more realistic scenarios, it starts to lead to alternative policy solutions that you wouldn't necessarily think of if you just looked at the ideal scenario. But I'll show this really quickly. So this is life expectancy at age 40 as it's estimated from this data. So conditional on survival to age 40, men here are expected to live another around 35 years based on these period conditions. And if I now move into this experiment where I bring all blood pressure down to 125, this jumps to 40, or a life expectancy gain of 5.3 years at age 40. So this is really pretty pronounced, and I think for anyone that works in mortality, a 5-year gain is quite large, especially attributable to kind of a singular risk factor. And I see the same thing for women. So women on average have a higher life expectancy, of course. But when I move to this world where I'm controlling blood pressure and bringing it down, it jumps to 43.6, or a gain of 6 years, so really large. So at least if you interpret this as a way of revealing the burden or importance of hypertension in this population, it would seem to suggest that at the population level, blood pressure is a really important factor for mortality here. But of course, I think this is important for establishing the importance of it in the population, but it doesn't speak to these more realistic scenarios. Like, can we really expect a 70-year-old to lower their blood pressure by 40 points? Yeah?
So just real quickly, do you know what the World Health Organization estimates were?
32.5 and 35.5. So my population on average is very slightly healthier, and that's something I will discuss. It's not exactly clear to me how that would interact with this estimate of the change, but the population is slightly healthier than the World Health Organization's estimates from that age. So I'm now showing the results over partial blood pressure control and compliance. So the contours here are the gains in life expectancy at age 40. And I'm showing it over 2 dimensions. On the x-axis, I'm varying the share of hypertensive individuals that actually reduce their blood pressure from 10% to 100%. And on the y-axis, I'm varying the size of blood pressure reductions in systolic blood pressure from 5 to 20 blood pressure points. And the big thing I want to show you is compared to that baseline of 5 years or 6 years, when we start to consider a range of more realistic scenarios, the results are a lot more sobering and a lot more modest. Across a large range of these, for example, if we say 60% of hypertensive individuals reduce their blood pressure by 15 points, we're only at a gain between 1 and 1.5 years. So it's very different than this very idealized scenario, and I think that's an important distinction because a lot of our current policy making is based on these GBD PAF style estimates that say things like you'll get 6 years of life expectancy back if you control blood pressure. And I think when you start to look at more realistic scenarios, I mean, by no means 1 to 2.5 years of life expectancy is by no means trivial, but I think it starts to help us think about potentially alternative strategies. And that's something I'll talk a little bit about in the discussion. So for women, there's a similar result, exactly the same. When you look at that ideal of 6 and then move to the more realistic scenarios, the gains in life expectancy are a lot less pronounced. It's a lot more modest now. So for example, if we take 50% of hypertensive women reduce their blood pressure by 10 points, we're actually only between about half a year and 1 year of life expectancy. So these, again, are not trivial, especially when you're thinking about life expectancy at age 40, but it seems to provide a little bit more sobering conclusion than in this world where everything is reduced down to the ideal level. Of course, none of this spoke to that question I raised earlier about are the benefits of blood pressure control really isolated among wealthier individuals? And the first way I looked at that was just to look at the age-standardized prevalence of hypertension by wealth quintiles, and this is for men. And here the wealth quintile is defined on an asset index, that's like what the DHS would use. And the big finding here is there really doesn't appear to be stark differences in hypertension across wealth. The level appears to be pretty flat and even across wealth quintiles. If we move to women now, the results are pretty similar. There does not really be any evidence that this is more concentrated among the wealthier individuals. If anything, it actually looks like the prevalence of hypertension is slightly higher among poor women. So right away, I think this goes against that really popular, strongly held notion that within poorer countries, hypertension is really more clustered among the wealthier segments of the population.
If people have medication that control their blood pressure, they will have lower blood pressure, right?
Yes.
So if the wealthy have higher prevalence or underlying risk of high blood pressure, they also have better access to medical care, then you get better.
Exactly, and that's something I will talk about, that it's evenness in purely measured blood pressure, but not necessarily evenness in terms of access to care or the fraction that take treatment. And if you look at the proportion of individuals that actually report taking treatment, it's the gradient you'd expect, where it's much more common among wealthier individuals. So, you'll have to take my word for it, but I go through this entire procedure of splitting the sample down by sex and wealth quintiles, going through this G-formula procedure again for the ideal scenario, and estimating the gains in life expectancy. And the thing I find is that for men and women across all wealth quintiles, the gains in life expectancy from that ideal scenario hover very cleanly around 5 years. So another way of thinking about this is the contribution of blood pressure to mortality at the population level seems to be pretty even across all these wealth quintiles. So of course, this is the thing that everyone's been alluding to already, that should you believe this result, I've given things so far a reasonably strong causal interpretation, and it really only provides a perfectly unbiased causal effect if there's no unobserved confounders. And that's something, of course, I can't test, and it's likely to be true. But rather than just abandon this question and say, I don't have causal identification, it's not worth doing, I'm going to adopt a slightly different perspective that's coming out of epidemiology and these methods of bias analyses. So specifically, I'm going to simulate the effect of an unobserved variable on the gains in life expectancy. And I do this by putting a little bit of structure to the unobserved variables. I assume that all unobserved variables can be represented by one dichotomous confounder with 2 sensitivity parameters. How strongly is this unobserved variable related to mortality? So if we want to conceptualize it as a comorbidity, how strongly is this comorbidity predictive of mortality? And the second one is how strong is the association between blood pressure and this comorbidity? So here, this is the strength of the association between the two. So by varying the levels of these 2 sensitivity parameters and recomputing the gains under these bias-adjusted scenarios, I think I have some sense for seeing how robust are these results from departures from the identifying assumption. Or do we really think that these levels of bias are plausible, the levels needed to negate the policy conclusions that are drawn from these findings? So that's what I'm going to show here. Again, the contours are gains in life expectancy, but I'll talk through the axes. The first here is this is the strength of the association between the unobserved variable and hypertension. So I'm considering an experiment now to lower blood pressure by 20 points. And here, this is the difference in the prevalence of the unobserved variable that 20 blood pressure point change would produce. So this is 50 percentage points, actually, not 50%. And on the y-axis, I'm varying the strength of the relationship between the unobserved variable and mortality. From no relationship up to this unobserved variable increases the risk of mortality by 25%. And so the way to think about this, you have to first benchmark it to the scenario where there's no bias. And in that scenario, the gain in life expectancy is around 2.4 years. And then evaluate, as you start departing from these identifying assumptions, how quickly do the gains drop off. And the big thing I want to highlight is across a wide range of these confounders, the gains in life expectancy stay pretty close to that 2.4-year benchmark. While they do decrease a little bit, they're certainly not decreasing so fast that we think the policy conclusions drawn from this are going to be overturned. Yeah?
So what's
Isn't the reverse, sorry. Isn't the reverse the scale?
No? Sorry.
Okay, go ahead.
so what's a variable? What's an example of an observed variable that raises the risk by
Chronic kidney disease.
1.25? Okay.
So of 1.25, yeah, chronic kidney disease I think would be a very good one. And chronic kidney disease is also related to blood pressure, so you could think of it as an important confounder. Yeah.
Are your standard errors changing much over the surface?
So the standard errors in this method don't change over the surface. You actually compute, because this is not doing it in a way that affects the errors. It's doing it that just affects the expectations. Yeah.
So this is a single binary confounder,
Right.
but you have more or less a continuous mean exposure variable.
Yeah, and this is more just a heuristic to value. The binary sorry, go ahead.
So if you essentially had something closer to a continuous distribution of the confounder, then you could make the entire effects go away. Right? I mean, it's going to be a limited effect simply because you're only using a binary confounder.
That's actually not true. The effect is, in some sense, yes, it is bounded by the fact that the confounder can't exceed more than 100%. You can either have or not have the confounder. But unless you're dealing with really non-normal distributions, you can think of it as like regressing the continuous unobserved confounder on an indicator and then using that indicator as the binary parameter. I'm happy to talk about this more afterwards. This is something I played around with for a long time. So I guess the thing that I take away from this is that there might still be an unobserved variable, but the magnitude of that unobserved variable would have to be really, really exceptionally large to change the conclusion I'm drawing that blood pressure is important for mortality at the population level here. I'm showing the same thing now for women. For women, it's slightly, the departures from this are slightly more sensitive, but the gains still stay within this 1.4 to 2.2 range for a wide range of these two parameters. So, of course, there's many important limitations. The first is this observational data problem. And I hope, maybe perhaps unsuccessfully, have tried to show you that the bias would have to be really large from unobserved variables to meaningfully change the conclusions that we're drawing from these data. The second thing, of course, is I only have a one-time measurement of blood pressure. So I could be masking kind of dynamic blood pressure treatment effects over time, but we typically think of those kind of things as biasing downward. So I think here it makes it somewhat conservative. And then there's this issue of missingness. Around 15% of the sample were missing due to blood pressure medication. And as I mentioned earlier, this 15% of people that are missing are on average the higher mortality individuals. That if you just compute mortality with the full sample without dropping anyone for blood pressure, life expectancy at age 40 is slightly lower. So it's actually not clear to me how this change in the sample selection would affect the size of life expectancy gains, but that's something I'm trying to explore by potentially trying to reweight this population or to look at other characteristics about them. But if people had thoughts on that, that's something I'd really like to know, because it's still not obvious to me how that would go. So I'd like to end now with a discussion of the findings and some of the conclusions from them. The first is this question I asked in the beginning about improving adult life expectancy. And the thing I find is that when you consider an idealized scenario, controlling blood pressure results in this very large gain of life expectancy, between 5 or 6 years at age 40. But when you consider more realistic scenarios, it really becomes far more modest, more sobering, between 1 and 2.5 years. And the reason I think this is important is it makes us maybe think about alternative treatment strategies. We might think about hybrid strategies that selectively target high-risk individuals, or coupling risk factors together, where you think of controlling BP as packaged along with tobacco cessation programs. And the reason I bring this up is the methodology here, this G-formula-based method, provides a really natural extension for these more complex intervention scenarios in a way that the population attributable fraction and typical results don't really allow for. So I think we can move towards, in future research, looking at more realistic ways of reducing mortality by considering more complex intervention effects. So the second So the second conclusion, of course, I find that the benefits are not isolated to the wealthy. And of course, this goes against a lot of that popular notion of hypertension as a problem of richer individuals. But as Magali alluded to, this lack of differences covers up or overshadows a lot of other differences. That there might be, or likely, large inequalities in access to blood pressure care or the ability to actually engage in treatment. And one interest of mine that's actually pervasive through a lot of my research is trying to understand why gradients in health emerge. And I think this is a case of a really potential explanation for why that happens. You have a scenario where blood pressure is kind of even between groups, but as blood pressure control becomes more prominent, if richer individuals are the ones that are more likely to take steps to control their blood pressure, we might see this change and expansion in inequality across groups over time. So this lets us think about policies or barriers to address policies that address barriers to control among lower SES groups. So I'll highlight 3 here, and I'll talk in the next slide about one that I'm actually working on right now. But the first is we might think of phone-based reminders. There's a large literature now in behavioral economics and psychology that's showing that poor individuals just have more cognitive decisions to make throughout the day. So they have their cognitive budget, if you will, is used up faster. So we might think of something as simple as just sending reminders as a way to potentially address that. Transportation costs could also be prohibitive for poorer individuals. If actually getting to the clinic and then purchasing blood pressure medication, that time and then going back for follow-ups could be too much. So we might think of either subsidizing these costs or just changing the delivery mechanism altogether and bringing, say, workers to households. Yeah?
I'm sorry. Just a quick question about the first bullet point.
Yep.
You found that wealthier people were already sort of more treated. I'm curious, but your sort of effect assumptions assume that you sort of just drop their blood pressure. I'm curious if you think that there's sort of an elasticity problem. If they're already more likely to be treated, you can't just shove more pills at them. And so
yeah, practically whether it's going to happen. But so I think if you're taking your blood pressure medication correctly, except in like kind of strange cases, you should be seeing gains of this size. So the fact that I showed you in that continuum thing that many people report taking medication, but very, very few of them actually have it under control, speaks to very, very poor compliance behavior. So I think that is a different issue, and it's not that they're taking medication, it's not working, we just need to triple their dosage. It's that they were given a course that they're not necessarily following. And so the last thing, and I think this might be particularly salient in poor countries, those with lower education may actually have false or inaccurate beliefs about treatment efficacy and their own survival probabilities. So if people don't think they're going to live very long and they think the treatment's not going to work, it's almost rational for them to not invest that much in health at their older ages. So I want to end now. I know we're going to spend some time talking about research, but I hope I can cover 3 things that are directly following from this project in particular. The first is this notion of addressing beliefs. And I think one finding that's coming out from a lot of these aging studies is that older individuals consistently underestimate their survival probabilities. If you ask them about their probability of surviving 1 year. So the problem is, of course, we might think that it would work, but we don't really have, in many cases, a good benchmark of what their best case scenario would be because of the lack of good adult mortality data in developing countries. So I'm working on this Halsey survey, which Harvard conducts, and it's a longitudinal cohort study that's nested within a health and demographic surveillance site in the Agincourt region of South Africa. And of course, that has the big advantage of we have now mortality estimates for that local area region. So I can actually construct adult mortality and compare mortality in that region to what people are responding on the individual level to see how much actual pessimism there is in survival, and see then if that's related over the course of this cohort study to things like investments in health at older ages. And while it's hard to think about that as getting the causal effect of beliefs, it might at least create a framework for thinking about intervening on those beliefs to try to correct them. The second thing is looking at the supply side of this, to look at how does the access and availability of care affect blood pressure control behavior. So here I'm doing work with Till Barninghausen at Heidelberg and Hans-Peter Kohler at Penn, and we're using a quasi-random rollout of health clinics in the Africa Center Health and Demographic Surveillance site, and using spatial and temporal variation in the rollout of these clinics to try to identify the effect of increasing access to care on a bunch of these blood pressure variables that we have. And of course, this I think is important for health policy, but the demographer in me wants to know how inequality emerges. And one really prominent hypothesis is that when you have things like access shocks, it's the richer individuals that take advantage of them, and that spurs this trajectory of inequality. So that's something we're going to look at here, is to see who are the actual people that are taking up or changing their behavior once they get this access to the clinic. And the final thing is something I'd love to talk more about. I just put in a grant with this with a couple other colleagues. We're trying to conduct a randomized control trial in Indonesia. I'm leaving next week to go to Indonesia to scope this. And our notion here is to go back to that first slide I showed you where I said 50% of adults are hypertensive. but only 30% are even aware that they're hypertensive. So right away, we might think that just improving diagnosis on its own might provide a way at the population level to kind of cheaply increase the proportion of the population that increases their blood pressure control. But there's a lot of pessimism about the ability of information to change behaviors. I think a lot of results from economics and health have shown that just providing individuals diagnostic information often, on average, has a zero effect. And my authors and I, our co-authors and I, we're taking a different perspective. We're saying that on average, it might be zero. But for some individuals, it's likely to result in positive behavior changes. So prior to this randomization of access, we're giving individuals a battery of both economic, behavioral economic, and psychological tests to measure things like risk aversion, time preference, and psychological characteristics like planning. And our goal is to then see, once we randomize on top of this, are there certain types of individuals that are more likely to take steps to control their blood pressure following this knowledge of information? And I think, again, this speaks to potentially this might be how inequality emerges. If only more advantaged people are initially likely to change their blood pressure after something like an information change. So I'd like to thank you and open up for questions. I look forward to your questions. I would be remiss if I didn't acknowledge a number of important people for this. So thank you so much.